Okay, so I'm going to show you how to do the first part of 10.3.1. But first, just so you can see, this is my Unit 3 note, my engineering notebook. First page is my rubric, second page is the calendar, then we have our review notes and our class notes. And here's 10.3.1. So our first challenge is to draw a breadboard schematic showing how the circuit diagram here would be wired. So my first step is to connect the positive terminal of the power source. And when I do that, this whole row is electrically connected to the positive terminal. Next, I will connect the negative terminal, the ground. And now that top row is electrically connected. And as you might remember, these top two rows here, and same with these bottom rows, are connected horizontally. I'll erase those. Woo! Didn't mean to do that. We'll erase these. But the middle rows are connected vertically. I should say the middle columns are connected vertically. And we call these top two rows the buses. They're connected to the power source. Okay, so looking at our circuit diagram, I am first going to add this loop here, which has the first resistor, R1. So I will add a jumper cable from the positive terminal to a column. And you can choose any column. I'm choosing this one because it's the closest, really. And then I'm going to add the first resistor, R1. Remember, this squiggly symbol represents a resistor. Here's R1. And we will connect that back to the ground. So to double check that I have a complete loop, I start at the positive terminal, come through R1, and then back to the ground. Okay, now we're going to add the second loop, which is here, goes through R2, R3, and back. And as we can see, R2 and R3 are wired in series with each other, but they are in parallel with R1. So on our breadboard schematic, this should look something like this. I'm going to add R2 here, R2, and you can see that this whole column is connected to the positive terminal. Now we'll add R3, which is in series with R2. Here, that's R3. And then we will connect that back to the ground. So to double check that that second loop is a complete closed loop, we start at the positive, come through R2, through R3, and back to ground. Wonderful. I'm going to erase that highlighting, and I'm going to erase this highlighting up here too. And that is our breadboard schematic. So now we're going to move on to part 2. And part 2 asks us to use Kirchoff's rules to fill in the table below for the circuit shown above. And for this problem, we have all the steps written out here. So we'll start with A. What is the resistance of each resistor? That one is easy peasy because we're given the resistance values. We can see that R1 is 5 ohms, R2 is 5 ohms, and R3 is 5 ohms. Easy. So we'll fill that into our table, and I'm going to write ohms up here. 5, 5, 5. Check. Check. B. What is the total equivalent resistance? And we find that by finding the equivalent resistance in each branch of our circuit. So we have two branches here. This first branch just has R1. Our second branch has R2 and R3. So let's write that below. We have R1, which we know equals 5 ohms. And then we'll find R equivalent of our second branch. And our second branch has R2 and R3. And since they are wired in series with each other, we simply add them. And we know that just because of what we know about series circuits. So R equivalent of the second branch equals 5 plus 5. That's R2 plus R3, which equals 10 ohms. Now, to find the total equivalent resistance, let's redraw this circuit. Let's simplify it. So now we have our power source connecting to our first branch, which just has R1, and then our second branch, which now, instead of having two resistors, I'm just going to say has R equivalent, and R equivalent represents R2 and R3. So to find total equivalent resistance, we can look at this and we know it's a parallel circuit. So we use this equation here. 1 over R equivalent total equals 1 over the resistance in each branch. So 1 over R1 plus 1 over R equivalent. And R equivalent is the equivalent resistance of the second branch. And since we're looking for R equivalent total, I'm going to rewrite that to look like this. R equivalent total equals 1 over R1 plus 1 over R equivalent. And now it's really just plug and chug. 1 over R1, which we calculated to be 5, or we were given that value, plus 1 over R equivalent, which is 10. Now you could use a calculator to do this, or just do it in your head. And I know that 1 over 5 equals 2 over 10. 2 over 10 plus 1 over 10 is 3 over 10. And 1 divided by 3 over 10 is 10 over 3, which equals 3.3333. I'll just say 3.3 ohms. So 3.3 ohms is our total equivalent resistance. And we don't need to write that in the table, but we are going to use it later on to find our current and voltage values for each individual component, in this case, for each resistor. What is the total current? Apply Ohm's law. So we know Ohm's law. It's V equals IR. Voltage equals current times resistance. And in this case, we're doing V total voltage equals the total current times R equivalent total, which we just calculated. And since we're solving for total current, I'm going to rewrite this as I total current equals V total over R equivalent total. Now it's just plug and chug. We know the total voltage, looking at our diagram, is 10 volts. So we'll plug that in, 10 volts, over the total equivalent resistance, which is 3.3 ohms. We just calculated that. And that equals 10 divided by 3.3 is 3. And this is current, so 3 amps. So 3 amps is our total current. And again, we don't need to write that in the table, but we will use it in our later calculations. Next step, what is the voltage across R1? So looking back at our circuit here, R1 is wired in parallel with R2 and R3. And we know that with parallel circuits, each branch gets the full voltage. So this first branch gets the full 10 volts, and there's only one resistor, R1, so R1 gets the full 10 volts. So I'm going to go ahead and write that in our table here. R1 gets the full 10 volts. And this second branch gets the full 10 volts, but R2 and R3 are going to share that 10 volts, and we'll deal with that later. So D, find the voltage across R1, just did that. Part E, what is the current through R1? Use Ohm's law. So looking at our table here, we know, well, I guess I'm telling you now, when you have 2 of the 3 cells filled in each row, you can easily find the third using Ohm's law. So for R1, we have resistance and we have voltage. So using Ohm's law, which is V equals IR, V1 equals I1 R1, we can solve for our missing component, which is current. I1 equals V1 over R1. And we'll just plug in those values. V voltage is 10 and resistance is 5. So the current across resistor 1 is 2 amps. So again, we just use Ohm's law to calculate current across resistor 1. Great. Part F. What is the current through R2 and R3? So looking back at our circuit, we know our total current. So we know, let's see, we start with our total current here, and then when we get to the node at C, our current splits. In parallel circuits, the current splits. And part of our current goes to R1, and the other part of our current goes down the second branch to R2 and R3. So we know our total current, and we know how much current R1 gets, and using those values, we can calculate how much current goes to R2 and R3. We know that R2 and R3 are going to get the same amount of current because they are wired in series with each other. So we can write our equation. This is the conservation of charge, Kirchoff's conservation of charge law. To write I total equals I1, the current in our first branch, plus I2, 3, the current in our second branch, the current going to resistor 2 and resistor 3. And since we're solving for the current in resistor 2 and resistor 3, I'm going to rearrange this equation by subtracting I1 to the other side. And then we simply plug in numbers. Our total current we calculated is 3 amps minus I1 we just calculated is 2 amps. That leaves us with 1 amp. So we have 1 amp across resistors 2 and 3. So let's write that in our table. Now you might be catching on to this. We have 2 of the 3 cells filled for R2 and R3, so we can calculate the third. We can calculate voltage for each of those. And we'll do that in part G. So V2 equals I2 times R2, and we're solving for voltage. Perfect. We know that I2 we just calculated is 1, and resistance is 5. So voltage is 5 volts. We'll write that in our table. And then V3 equals I3 times R3. We just calculated the current across resistor 3 is 1. We know the resistance of resistor 3 is 5 ohms. And again, we get 5 volts. Okay, part 3, I'll just do A and then I'll let you finish the rest. So what would the current be just after the following points, and justify your answer? Point A. What would the current be just after point A? Well, the current does not have anywhere to split off before it gets to point A. So A is going to get the total amount of current, which we calculated is 3 amps. So I would write here 3 amps, and my justification is the current has not split. The current has not split off yet. Okay, I'll let you finish those ones on your own. And just to note, for the second half of this worksheet, we did not write out the steps to calculate resistance, current, and voltage for each resistor, but you can refer back to that first problem and follow our process. But just in general, when you're analyzing a circuit like this, there's a process to follow. I'm going to add a sticky here. So the first step is always to calculate your total equivalent resistance. Next step is to use Ohm's law to find the total current. I'll even write that. Find the total current. So when you do that, you would use the total voltage and the total resistance, total equivalent resistance. Then finally, you'll use Kirchoff's laws, which we have the loop rule. The sum of voltage in any loop equals 0, and conservation of charge. Okie dokie. Well, move on to the second problem and let us know if you have any questions. Thank you for watching.